Okay, we will go through some important points in the class 12 physics, chapter 3 current electricity. Okay, and the charges in motion constitute the electric current. Such a currents occur naturally in many situations. Lightning is one of such a phenomenon in which charges flow from clouds to the earth through atmosphere. Okay, charges flow from clouds to the earth through the atmosphere during the lightning. Okay, current at time t across the cross section of the conductor. Current at time t across the cross section of the conductor. In SI unit, the unit of current is in amperes. Okay. See how much is the lightning current carries the order of the tens of thousands of amperes. That lightning current is tens of thousands of amperes, but in our nerve current is in the microamperes. Okay, that is tens and thousands of amperes, but in our nerves it is in the order of microamperes. Okay, the ionosphere, the charged particle do exist in the upper parts of the atmosphere called ionosphere. Okay, 1 gram of water contains approximately 10 power 22 molecules. If you consider the solid conductors, the charge carriers are negatively charged electrons as the charge carriers in conductor. But in electrolytic solutions, the positive and negative charges both can move. Okay. In conductor only electrons are the charge carrier, but in electrolytic solution both positive and negative charges can move. Okay, the electrons in the conductor drift due to the electric field. We have a plus q and minus q, then electron will charges plus q and minus q put at the end of the metallic cylinder. So this is like a conductor. The electrons will drift because of the electric field created to neutralize the charges. Okay. Here they are given pictorially how the resistance varies based on the dimension, how it varies with the cross section, how it varies with the length. Okay. Ohm's law, V equal to Ri. V is the voltage, R is the resistance of the conductor, I is the current. R is the resistance of the conductor. Resistance means is opposed the current flow. Okay, resisting the current flow. Resistance. Not only depends on the material of the conductor, but also the dimension of the conductor. The resistance depends on the dimension of the conductor also. The resistance is proportional to the length. Okay, is directly proportional to the length. More length means more resistance. It means. See here they given how resistance varies with dimension. Thus, solving the area of cross section of the conductor. Area of cross section of the conductor doubles the resistance. Okay. When the area of cross section is small, the resistance will be more. In general, the resistance R is inversely proportional to the cross sectional area. Is directly proportional to the length and inversely proportional to the cross sectional area. So, see here the rho, this is the constant of proportionality and it's called resistivity. It depends on the material of the conductor but not on the dimension. Okay, the resistivity depends on the material of the conductor and not on the dimension. Okay, current per unit area taken normal to the current is called current density and is denoted by J. Okay, current per unit area is current density. Charge density is called the current density or charge density is denoted by G. J is the current density, rho is the resistivity. E electric field equal to J with the electrical resistivity. Okay, conductivity is equal to 1 by resistivity. Conductivity equal to 1 by rho is called conductivity equal 1 by resistivity. Acceleration electrons in the electric field. See here how the electron drift takes the path. This is solid line is the normal drift and dashed line due to electric field. Okay, dotted line full lines without electric field and dotted line with the electric field. So here they mentioned what is the drift velocity. Okay, drift velocity. The electrons move with the average velocity which is independent of the time. Although electrons are accelerated, this phenomena is called drift and drift velocity. See here the electric field in this direction, current in a metallic conductor. Okay, the magnitude and current is contained in the cylinder. Okay. Normal to A. Normal to the cross section means it is parallel to the this area. Here how conductivity is related to the relaxation time. N is the number of carriers, E is the charge, electron charge, M is the mass of the electron. Electric tip is opposite to the electric field direction. Okay. The direction of the drift velocity of the conduction electrons is opposite to the electric field direction. Electron drift in the direction of increasing potential. So here this N is equal to the number of atoms per cubic meter. Number of free electrons per unit volume. Compare drift speed with the thermal speed and electric field. Here they are given the comparison here. So note that the drift speed of electrons is much smaller, about 10 power minus 5 times typical thermal speed of the ordinary temperature. Okay, drift speed is much less than the thermal speed. Thermal speed versus drift speed. And electric field traveling along the conductor as a feed of the electromagnetic wave. Normally this 3 into 10 power 8 meter per second. So the drift speed is in comparison extremely small by the factor of this. See why there is no acceleration. Due to the repeated collision it loses its speed, so that is why there is no acceleration. No acceleration because of the collisions. Okay, it loses the drift speed after collision but starts accelerate and again there is a collision. In the absence of the electric field, the electron travels in the straight line, but in the presence of the electrical paths are in general or curve. The mobility is defined as the magnitude of drift velocity per unit electric field. Mobility is the magnitude of the drift velocity per unit electric field. Okay, here blue line is for the good conductor. The dashed line represents linear Ohm's law. The solid line is the voltage versus current for the good conductor. Good conductor, and the dashed line for linear Ohm's law. So note here this here the unit of x-axis here is different and this side is different. Resistivity of the various materials for conductor, insulator and semiconductor. Semiconductor have low resistivity, electrostatically decreasing with rise in temperature. Okay, semiconductor have low resistivity. Effect of temperature and resistivity for the conductor is for resistivity and effect of temperature for the semiconductors and for the insulators. Okay. Resistor in the higher range are made mostly from carbon. Carbon resistor have the higher resistance. The carbon resistor are compact, inexpensive, and thus find extensive use in electronic circuits. Carbon resistance. This is how you remember the color code of the resistance. B Roy of Great Britain has a very good wife. So you have to B mean first B black, second B brown, and R red. Then in between next G is coming, great green. So this orange yellow you have to remember. Okay. So when they say this is the resistance, 36 into 10 power 4 ohm means, so first 3 is for orange, 6 blue, and the 10 power 4 yellow, and with 5% tolerance gold. Okay. Orange. Temperature depends on temperature dependence of the resistance. This is how resistivity varies with the temperature. Alpha is the temperature coefficient of resistivity here. This alpha. This is how the resistivity varies with temperature for the copper, and this is for the nichrome, and this is for the semiconductor. Resistivity, how it varies with the temperature. Unlike metal, the resistance of the semiconductor decreases with the increasing temperature. Conductors resistivity increases with the temperature, but semiconductor decreases with the temperature, increase in temperature. Depends inversely upon the number of free electrons per unit volume. The steady temperature of the heating element when heating effect due to the current equals to the heat loss due to the surroundings. So you can go through that example. Current into time is the total charge. The kinetic energy and potential energy is conserved. Kinetic energy increases in the direction of the electric field. Okay. Thus, in case charges are moving freely through the conductor under the action of the electric field, their kinetic energy would increase as they move. So, kinetic energy increases the electric field direction. Okay. Power dissipated in the conductor P equal to I square R. Okay, V equal to IR, voltage equal to current into resistance, but power equal to current square into resistance. So from this formula we can suppose power is given, current is given, we can find the resistance. Power is given, resistance is given, we can find the current. So in the cell, chemical energy of the cell which supplies power to the it supplies the power. Okay, this chemical energy of the cell is supplies power. The energy dissipated in the resistor comes from the chemical energy of the electrolyte. Okay. Combination of the resistors. When we connect resistors in series and parallel. Okay. Series combination of resistors R1 and R2. Series combination just addition of the resistors. Okay. You have R1 plus R2 plus R3 when you connect series. This is how you connect resistors in parallel. So both end of the resistors you tie together, and the other end also you tie together. These two are in parallel. So you will find the equivalent resistance when they connected in the series. Equivalent resistance R1 plus R2 and resistance you connect in series means you have to simply add all the resistance. When you connect in parallel, 1 by R equivalent equal to 1 by R1 plus 1 by R2, the two resistance. Similarly, connect N resistance, it will be 1 by R1 plus 1 by R2 plus R2. But if you connect capacitors in parallel, then you got to simply add C1 plus C2. Capacitor resistor, that is a difference. Okay, these are parallel capacitor, parallel resistance. This is the equivalent resistance when the when the resistors are connected in parallel. 1 by 3 resistors are connected in parallel. See, this resistance is connected, these two are in parallel. So you have to first to find the equivalent resistance of these two. That is this resistance. Then you have to add they now both are in series. Then you add total resistance. Okay, cells EMF internal resistance. Okay, here we have a positive electrode, negative electrode. The difference is the potential difference V between the electrode. Okay, this is the direction of the current from positive electrode to the negative electrode flows. Okay. See here, you see clearly across the electrolyte the same current flows through the electrolyte, but from N to P, whereas through R it flows from P to N. Okay, through resistance, in this resistance current flows from positive to negative, but within the electrolyte it flows from the N to P. Okay, within this electrolytic solution, that is what they are mentioning. Okay, within the whereas electrolytic solution from negative to the positive electrode. Note the negative sign in the expression here. Okay, negative sign in the expression for the potential difference between A and B. This is because current flows from B to A. Current flows from B to A in the electrolyte. In practical calculation, internal resistance of the cell may be neglected. The current I is such that this is much greater than this IR. Maximum that can be drawn from a cell is for R equal to 0, and it is maximum. Okay, and resistance is 0, the maximum current will flow. So this is the internal resistance, this one. So now these two are in parallel and these two are in parallel. After that all the three will be in series. So they are finding the equivalent resistance for the first parallel combination. This is for the second parallel combination. Then they are adding without including the internal resistance. Now they are including internal resistance here 1 ohm while finding the current. See, when you have parallel resistor, the voltage drop will be same across the resistor. Okay, here the voltage drop across 4 ohm is same as this 4 ohm. Voltage drop across 12 ohm is same as across 6 ohm. That means current will be different. Okay. Total voltage. Okay, the same principle, effect of the internal resistance. How when we connect in cells in series and parallel, what is the effective voltage? This is the equivalent voltage when we connected in series, and the equivalent internal resistance when connected in series. Connected to negatives. When cell connected in series, the equivalent EMF of series combination cell is just the sum of their individual EMF. The equivalent internal resistance of the series of combination of N cell is sum of their internal resistance. This is how you connect in parallel. So this is equivalent EMF and equivalent resistance when you connect in parallel. Kirchhoff's rules. See here, Kirchhoff, there is a current rule. Current rule, that is junction incoming and outgoing currents. When you add incoming and outgoing current, the resultant will be 0. Sigma I will be 0. That is the law of conservation of charge. Okay, junction rule. There is a energy rule, loop rule also is there. That is the conservation of the energy. Okay, so here in this loop, there is incoming current I3 that is equal to the outgoing current I1 plus I2. So I3 equal to I1 plus I2. When you add all the currents in this junction, then it will be 0. So that means incoming current will be positive sign, outgoing current will have a negative sign. So you add all the, that will be 0. Similarly, for this loop we can do the voltage equation also. That is the loop rule. That is the conservation of the energy. Okay, at any junction the sum of the current entering the junction is equal to the sum of the currents leaving the junction. Okay, that is the junction rule. Loop rule, the algebraic sum of the charges in the potential around any closed loop involving the resistors and cells in the loop is 0. So this is the complex circuit. Here they can find the resistance using the given current and EMF of this battery. So you don't have to worry about this circuit. Here using the current and voltage, you can find the resistance of this circuit, equal resistance. So here this is how they found. This is the loop rule. Okay, this loop is for this loop here, 10 volt, A, B, C, C dash and EA. This voltage minus potential drop across this resistance and this resistance and this resistance will be 0. Okay. Okay, this is the EMF of this cell. This is the voltage drop across those three resistors. When you add up this, all the three, then will be 0. That is the loop rule. Conservation of energy. Okay, here this is the loop 1, loop 2 and loop 3. In loop 1, this current is opposite to this current. This is the direction of the current. So this voltage, the voltage drop will be negative in the direction of the current, but it will be positive in the opposite direction. Okay, 10 minus this voltage, but plus this voltage 2 across 2 ohm, it will be plus, because this current direction is opposite to this current direction. See here, negative, this is along the current direction, but here this is opposite to the current direction, plus 2, minus 4 along the direction of the current, plus 2 opposite to the direction of current, so you are using plus. Sum of loop voltage, a plus sign drop against the loop direction, minus sign use the along the loop direction. When the bridge is, this is how you find the unknown resistance. This is a unknown resistance and this is a variable resistance ended on. When there is no current through this galvanometer, that means the bridge is balanced. That is, balanced bridge means R2 by R1 equal to R4 by R3. That is the balance condition. So this current will be equal to this current, that is I2 will be equal to I4, I1 equal to I3, equal currents. When potential at B equal to potential at D, then when these two are at the same potential, B and D, then there will not be any current through Z. That is the balanced condition. So you have R2 by R1 equal to R4 by R3. This last equation relating to force is called the balance condition for galvanometer to give zero or null deflection. So R3 is the variable resistance here. Okay, this is what we vary till we get a zero here. That is how we will find the unknown resistance. This is the final equation. So this is the meter bridge. It's like a Wheatstone bridge only. So here meter bridge means this resistance length is 1 meter, that is 100 centimeter, and the resistance per centimeter is same. Suppose we find 4 centimeter, mean per centimeter how much resistance, then 4 into that much resistance is this resistance across this L1. This will be 100 minus L1. Okay, here also R by S equal to L1 by 100 minus L1. That is the balance condition. So this is R by S equal to L1 by 100. This is the balance condition. When we have to find L1, then unknown resistance will be found using this. This is S is the standard resistance. That is the variable we are varying. Then from L1, known L1, we can find the unknown resistance R. See here, that is important. For better accuracy, the ratio of R by S should be nearly 1. That is, the null point should be near center of that meter scale, around 50 centimeter. Okay, so you have to choose that resistance accordingly. Okay, so you have to choose the resistance accordingly. R by S equal to L1 by 100 minus L1. Resistance in parallel, they are computing the equivalent resistance like this. Potentiometer, this is a versatile instrument. It's basically long piece of uniform wire, sometimes few meter length, with the standard cell B is connected. Variable resistance R. This is the variable resistance, and this will be varied with this condition. Okay, choosing the value of R. So when you want to compare the EMF of this cell, so this value of the R you have to adjust such that choosing the value of R variable is so that the potential drop across N is slightly greater than E1. So across N1, that is from this A to N1, potential difference across this N1 should be slightly greater than the E1. So accordingly we have to adjust the value of this variable resistance. That is the potentiometer condition. Otherwise you may not get the null point here. This is how you, for internal resistance, finding the internal resistance. This is for finding the EMF. Or internal resistance equal to variable resistance. This is a comparison. Okay, for parallel resistance, remaining resistance of the potentiometer. Okay, can go through the summary also. The current density. These are the units and dimensions. Okay.